Chapter 9, Section 3, we are going to be looking at probabilities. And you have been introduced to probabilities in the past. So let's look at these definitions. When we deal with probabilities, we talk about a sample space. If we're talking about a dice, I don't have any, or a die, I don't have any die up there. But the sample space of the die are all the possible things that can happen when you roll a die, which happen to be these 6 numbers. So there's the sample space for that event. An event is one action that you're doing. You're rolling a die, you're flipping a coin, you're choosing a person out of a crowd, whatever it is. The event is that one action that you're doing. And generally when we talk about probabilities, we like to start with equally likely outcomes. And when you roll a die, if it's a fair die, you should have an equal chance of rolling any of those numbers. Those are just terms that we use. Probability, then, is a ratio of the number of outcomes in the event that you want to get over the total number of outcomes in the sample space. So what's the probability that you will roll a 2 when you roll one die? How many ways can you get the number 2? One way. And how many total outcomes can you have when you roll a die?
6.
There's our probability that we can roll a 2. 1 out of 6. 1/6. So probability, the ratio of the number of outcomes in the event that you want. E is the event that you want, and the total number of outcomes in the sample space. So testing your intuition about probabilities. Find the probability of each of the following events, tossing a head on one toss of a fair coin. What's the probability? 1/2, 1/2. 50%, we usually write probabilities as fractions when we start off, or decimals. They can be written as percents. Tossing 2 heads in a row on 2 tosses of a fair coin. What do you think? I mean, right now we're just guessing. 1/4? So what's the probability that you will toss 1 head the first time you do it? 1/2, 1/2. What's the probability the second time you'll do it, you'll toss 1 head? 1/2. We are going to learn, even though we haven't done it here, when you want to do 2 things, this and that, you multiply them together. So 1/4 is the correct answer. Now, we could set up our sample space. Let's look at this for just a little bit. If I would set up the sample space, I might toss tails and then tails. That's one thing I could do. Tails and then heads. I could toss heads and then tails. I could toss heads and then heads. Those are all the possible outcomes I could do. How many of them are 2 heads? 1 out of the 4. So that's how it works with the sample space. There's one way we can get that event. These are all the possible outcomes. So that's our sample space. Drawing a queen from a standard deck of 52 cards. Now sometimes these are called face cards, not picture cards, depending on who you're talking to. What do you say? Drawing a queen. There are 4 queens out of 52 cards, and I reduce it down to 1/13. 1/13, there's a probability to do that. Rolling a sum of 4 on a single roll of 2 fair dice. Notice we're not going to have unfair dice when we do these things. What's that probability?
4.
Now what I would do is I would start listing the ways my event can occur. I could roll a 1 and a
3.
1 and a 3. I could roll a 2 and a 2. I could roll a 3 and a 1.
Would you say 2 and 2 again?
And I would say 2 and 2 again. Why? Would I say 2? I shouldn't say I would say. Would I say 2 and 2 again? The first one you roll 2. Second one you roll a 2. Is it a different roll by saying another 2 on this first die? There's only one 2 on it. It's not a different roll. You wouldn't. You wouldn't, because you're rolling just 2 die. You can only get 1, 2,
You would
and
put
1,
1
2.
3 and 3 and 1 because it's different.
You would, because one might get a 1 and the other a 3, or this one a 3 and that one a 1. So there are 3 ways we can get it. Now we need to know how many total ways I can roll.
6 and 6,
Yeah.
6 and 6.
6 and 6. There's 6 things here, 6 things here. 6 times 6 is 36, which would reduce to another 12. There'd be a probability of that one. Guessing, we're going to play the lottery over here. Guessing all 6 numbers in a state lottery that requires you to pick 6 numbers between 1 and 46 inclusive. Well, what is the event that we want to happen?
Pick 6.
The right numbers is the event. How many right numbers are there?
Do I have 1?
There's one set of right numbers.
Oh.
I kind of asked the question poorly. There's one set of right numbers. So my event is only one thing. Now what is the total value in my sample space? How many groups of 6
So one
can we
set
select?
is one number 5 different numbers. So the order is 5 and 1.
The order does not matter on this one because they didn't say it here. This is actually the same question as we had earlier, where they actually always have it in the same order. That's the question to ask. Does order matter? For this question, it doesn't. It just has to be the right group of 6 numbers. So it would be a combination. I don't know what your calculators say.
Isn't it small so largest and water?
I don't know. They're saying this one is. Truthfully, I just never buy lottery tickets. I haven't either. It's just a waste of money, so I've just never done one.
5,366,890.
800 and what? 19. So not high. We know that already. That's not the way to make your money, like the lottery. I did have one time Christmas gift exchange, and somebody gave me some lottery tickets, but truthfully, I don't remember what they were at all, so I don't know if they're always in order. Testing a probability function. Now, I am missing something from what I said up here. Oh, maybe that's on another page. Okay. Is it possible to weight a standard 6-sided die in such a way that the probability of rolling each number, we're going to call the number n, is this, 1 divided by n squared plus 1? Well, probability functions, all the probabilities have to add up to 1, or 100%. All the possible things that might occur, when I put them all together, one of those things has to occur. I have to have a 100% chance of doing one of those events. If you think of just flipping a coin, we only have 2 things, heads or tails, and I have 1/2 chance of flipping a heads, this is 1 flip, and 1/2 chance of flipping tails, and if you add 1/2 and 1/2, you get 1. All probabilities have to work that way. The total of all the possible outcomes must be 1, or 100%. So that's what I do to test to see whether a function they have given me actually can be a probability function. So they're saying, okay, you roll a 1. Well, if I use this function right over here, if I'm using this function, that would be 1 over 1 squared plus 1, which is 1 over 2. And if I do a 2, 1 over 2 squared plus 1, that'd be 1/5. 1/5. I'm not leaving myself enough room, am I? If I do a 3, 3 squared plus 1 is 10, 1/10. 1/10. Here's my next one. If I do a 4, 4 squared plus 1 is 17, so 1/17. And a 5, 5 squared plus 1 is 26. And 6 is 1/37. Add those up on your calculator. A 1/2 plus a 1/5 plus a 10th plus a 17th plus a 26 plus a 37th. We want to know, will that equal 100%? Since those are all the possible things I could roll. Or 1. What'd you get?
0.92.
Yeah,
0.92? It is not possible to have probabilities with that formula because you've done all the events and it doesn't add up to 100%. So our answer is no. Probability functions must add to 100% or they don't work. It's not really true. It's not really a good probability. So when we determine probabilities, what do we try to do? Well, sometimes we're going to look for the sample space. What's all the possible? And then list these equally likely outcomes to figure out what we had. This is our formula. We've gone over the formula. That's the formula that we're going to do. They don't have to have equally likely outcomes, they're saying down here. If I am rolling 2 die, you're not equally likely to roll every possible outcome. There's only one way to roll a 2 with 2 die, 1 and 1. But to roll a 3, there are 2 ways, a 1 and a 3. To roll a 4, there are 2 ways, a 1 and a 3 and a 1. So my outcomes don't all have to be equally likely, but whatever the outcomes are, they have to satisfy the fact that if you add all the probabilities, it has to be 1. So let's try this same problem done 2 different ways, and both of them are equally valid. Sal opens a box of a dozen chocolate creams, generously offers 2 of them to Val. Val likes vanilla creams the best, but all the chocolates look alike on the outside. Do you have one of those mothers who you get a thing of chocolates and they pick them up, they take a bite, they look at it, oh, I don't want that one. Then they pick this one. I don't know if you have one of those mothers or not. But anyhow, my mother's not like that one, but I have known people that way. Or they open them up and they poke on the bottom of them, and then they don't like it, they set it back down. It's like, are you kidding me? All right. So what does Val like? Vanilla creams over here, but they all look alike on the outside. If 4 of the 12 are vanilla, what's the probability that both of Val's picks are going to be vanilla? So I'm going to first think of how can I get the total number of ways I get what I want, my event, and how can I get the total number of ways that I might get an outcome from this, my sample space. Well, the event I want is to get 2 cream vanillas. 2 of them, right, that are vanillas. Well, there are 4 vanillas available. So the number of ways I can get 2 vanillas is a combination from 4, I want to choose 2. That's the total number of ways I can get 2 vanillas. And I can only get them from the 4 vanillas. I can't get them from the other 8 that are something else. Now, what are the total number of ways I can draw 2? Because we're taking 2 of them out. Well, total is there are 12 creams available. I'm choosing 2 from the 12. That's my total. Run your calculators. What do you get for this? And go ahead and give me the number on the top. 6 on top? 4 choose 2 is 6? Okay. And 66? So if we reduce that, we get 111, right? And you can divide and get a decimal. So there's one way of doing this. There's a second way of looking at it. Now this way I figured out the total number of ways using a combination, total number of ways using a combination. There's a second way. If event A has probability piece of 1, and event B has probability piece of 2, and I want to do A and B both together, we just multiply them. We actually used that earlier before we said this last year. We just multiply the events. So I'm going to take this idea, one thing happening after the other. Same question. There are a total of 12 creams. And 4 of them are and 4 of them are the vanilla that she wants. Well, if she draws 1 of them, what's the probability that that 1 is a vanilla one? 4 out of 12. There are 4 ways that we can get what she wants out of the 12. Times, now we're going to do it the second time, assuming she drew a cream vanilla. What's the probability the next time when she reaches it in? 3 out of 11. There are 3 ways to get what she wants now there's a total of 11 because 1 is gone. Well, if I multiplied this together, 4 times 3 is 12. 12 times 11 is 132. Is that right?
Yeah.
And if I divided this by 12, same answer. So both of these are valid. You can think of it either way. You will get the same answer. Another way to work with probabilities is drawing diagrams. A Venn diagram is where you represent the total number of things in 2 or more categories. So maybe I have people playing sports. So everybody who plays sports is represented by the blue circle. Girls I have in my group are the yellow circle. What would be this overlapping region in the middle?
Girls.
Girls who play sports. Now, this box represents my whole group. So what would this region outside of the yellow circle represent?
Boys.
Boys. Outside of the yellow circle and the blue circle.
Boys that don't play.
Boys who do not play sports. Right. And then the box represents everybody in the group. Venn diagrams. Sometimes we use those. Sometimes tree diagrams. So if I have 2 jars, well, I'm going to start with, right here is where I begin, and I have 2 choices. So what are the probabilities I would draw either of these jars? Well, I have a 1/2 chance to draw jar A and a 1/2 chance to draw jar B. Then I'm over here and I'm in jar A. What's the there happen to be 4, these are cookies in these jars. What's the probability? Well, there's 1/4 probability I would draw any one of them. 1/4, 1/4. Well, if I'm down here in jar B, what's the probability I would draw this one cookie, which is the only one there? 100%, 1 on that one. And then if I wanted to know the probability of exactly choosing this cookie, well, I first have to choose jar A and then choose this cookie. 1/2 times 1/4. 1/2 times 1/4. I have a 1/8 chance of choosing that cookie, just using the idea of multiplying the probabilities together. So tree diagrams sometimes are useful. So every one of these would be 1/8, and 1/8, and 1/8. What would be the probability of choosing that chocolate chip cookie? 1/2. 1/2 times 1, 1/2. You have a 1/2 chance, 50% chance you're going to choose that cookie. All right, let's try a Venn diagram one down here with some values. In a large high school, 54% of the students are girls. So girls, that's my yellow. 54% are girls. 62% of the students play sports. Okay, so everybody who plays sports is here. So my blue is 62%. Half of the girls at the school play sports. So if half of them play sports, then that means 27% of the school are girls who play sports. And 27% of the school are girls who do not play sports. So that 54 here is all the girls, the blue. If students, well, let's keep going with this, actually. Can you tell me what percent I have out here that are boys in the white who do not play sports? Well, how much are used up totally in these 2 groups?
It's 27 plus 62.
27 plus 62 are used up in the girls and sports playing people, because some of them are overlap, girls who play sports. 62 is the whole blue plus 27 over here. So what is 27 plus 62? 89. So I know I have,
89.
whoops.
So 100 minus.
So I need to take 100 minus 89. This equals 89. So if I take 100 minus 89, what do I have left over for the boys who don't play sports? I have 11% are boys who don't play sports. Just building up from this Venn diagram. If a student is chosen at random, what's the probability as a boy who does not play sports? 11%. I just did it from the picture. What percentage of the students who play sports are boys? So we want them to play sports and we want them to be boys.
62 minus.
Yeah. This region out here are the boys who play sports. So 62% of the school play sports and 27% of them are girls who play sports. And that means 62 minus 27 must be the boys who play sports. What is that? 35% of the school are boys who play sports. So a Venn diagram is sometimes useful. Let's do that tree diagram up here with these cookies. 2 identical cookie jars on a counter. Jar A contains 2 chocolate chip and 2 peanut butter, so there they are. Jar B just contains 1 chocolate chip. So we're going to select a cookie at random. What's the probability that it happens to be a chocolate chip cookie? Well, if we're going through this again, we know we have a 1/2 chance of doing either jar. And then we know every single one of these, if we're in this jar A, we have 1/4 chance to draw any of those. And 1/2 times 1/4 is 1/8. So every one of these cookies, we have a 1/8 chance of drawing those cookies. If we're in jar B, 100% chance of doing that one, so we have a 1/2 chance of doing that. So a chocolate chip cookie. Well, I could have this one, or this one, or this one. 1/8 plus, or I could do this or this. I'm not drawing this one and this one and wanting to know that probability. We add in that case. 1/8 and what does that have? 1/2? Well, 1/8 and 1/8 is 2/8 plus 4/8 equals 6/8 equals, there's my probability of drawing a chocolate chip cookie, because it can be any one of those 3 chocolate chips. So I just add those probabilities together. Conditional probability. Conditional is when it's dependent upon you doing something else first. The only way I can draw a peanut butter cookie is if I first select jar A, because I can't get any peanut butter cookies from jar B. So conditional probabilities are built upon being dependent of something else happening first. And how we write it, let me read it right here. The probability of drawing a chocolate chip cookie given, that straight line there we read given it's from jar A. Well, probability of a chocolate chip given, we've already drawn jar A. Well, if I've already drawn jar A, what's the probability of getting a chocolate chip? 2 out of the 4, 1/2. So that's where they got this from. Given I already drew from jar A. Probability of getting a chocolate chip cookie, given that you already did jar B. Well, if I already did jar B, what's the probability of getting a chocolate chip cookie? It's 100%, 1. It's the only thing I can get. So that slash, it's a conditional probability, read given. Probability of the first thing, given the second thing has already occurred or already happened. Probability of A given B. Probability of A given B. Meaning probability of event A given that event B occurred, already happened. So there's a formula for conditional probabilities. And using A and B, and then they switched it down here. They used AB there, then they used BA down here. Probability of B given A occurs is the probability of event A, that first event that we want to occur, and the probability that B happens given event A has occurred, divided by the probability of that first event happening. Let's try that function out, try that equation out, that formula out. Suppose we have drawn a cookie at random from one of the jars described in example 7. Given it is a chocolate chip cookie, what is the probability that it came from jar A? So how I would write this is probability of jar A. Maybe I should not use A because we'll mix it up with it there. Jar A given its chocolate chip. That's how we write what they said there. Okay, so if I'm going to do this formula, then I need to do the probability of the second thing and then the first thing occurring from that second thing. So the probability of drawing a chocolate chip and it being from jar A. Well, the probability of drawing a chocolate chip is 2 out of 4 when it has come from jar A. So 2/4 or 1/2. That's the top part. Divided by the probability I draw a chocolate chip. Well, earlier we figured out the probability of drawing any chocolate chip cookie. 3/4 was that probability. Well, instead of dividing by 3/4, we're going to take that 1/2 and multiply by 4/3. That's not the right answer. 2/3. What did I do wrong? That's terrible. I don't think that's the right answer. I remember going through this. What is that? Example 8? I can look in the book real quick. Oh, yeah, I forgot to do this. Okay. Probability of A and B up here. So I need to have the probability of chocolate chip and drawing jar A. Well, I have a 1/2 probability of getting a chocolate chip from jar A. But I also need to draw jar A, 1/2. So what this is, probability of getting a chocolate chip from jar A is 2 out of 4, 1/2. And the probability I draw jar A, which is 1/2. So 1/2 times 1/2, that goes on the top. And 1/2 times 1/2 is 1/4. And instead of dividing by 3/4, we'll multiply by 4/3. And that gives me what I was wanting to get, 1/3 probability. When we have specific two outcomes, what does the prefix by mean? Two. Two outcome, we have a formula for figuring out how many events happen. What are two outcome events? Maybe they're true and false on a test. Maybe they're yes and no. Maybe they're heads and tails. Maybe they're you made the basket or you did not make the basket. Maybe it is you have a boy or you have a girl. It's a lot of things are binomial. You got the answer right on the test, you got the answer wrong on the test. There's a lot of binomial things that we can do. So we can use a binomial distribution in order to get an answer for the probabilities of two outcome events. And the binomial distribution and the binomial theorem, you recognize that thing right over there? That looks kind of familiar. A combination. N choose R. Now what this rest of the stuff stands for, the P is the probability of getting what you want. Q, P is what you want, probability of what you want. Q is the probability of not getting what you want. And when there's two outcomes, it's easy to figure out if I have a 30% chance of getting what I want, what's the percent of not getting what I want? 70. So it's always complements of each other that add up to 1. And then this N and R means N is the number of times you're going to do it. This is the number total of times you're going to do whatever's happening. And this is the number of times you get what you want. So if I am, let's say I'm shooting baskets, I'm shooting free throws, I'm shooting free throws 10 times in a row. I want to make 9 out of the 10. If I want to make 9 out of the 10, it would be 10, choose 9. Total number of times I'm going to do it is 10. 9 times is how many I want to make the basket. Then I need to multiply it by the probability I make the free throw. Well, if you play basketball, everybody keeps stats. Oh, they're a 75% free throw shooter. So I know the probability, 75%, 0.75. And I raise that to the same power as the number of times I want to make it happen. I raise it to the 9th. Now, if I'm a 75% free throw shooter, what's the percent that I don't make it? 0.25. 0.25. And this exponent is the leftover, N minus R. 10 times, I'm going to make it 9 times. Well, there's only 1 time I'm going to miss it. There's the formula. And you do that formula, that will tell me what your probability of making 9 out of 10 free throws are. So trying that idea right down here. We roll a fair die 4 times. Find the probability that every single one of them is 3s. So for part A, I want to roll it 4 times. I want all 4 of them to be what I want. What's the probability of rolling 1 3? You're rolling a die. 1 over 6. 1/6. And I'm going to raise that to the 4th power because I want all of them to be that 3. What's the probability you do not roll a 3? 5 over 6. And 0 times I want that to happen because all 4 of them. I don't know, your calculators. This is a combination. 4 choose 4, that's actually 1. And anything to the 0 is 1. So really all you have to do is 1/6 raised to the 4th power. Go ahead and give me the decimal.
Uh, 7.71 times to the negative 4.
10 to the negative 4th? 0.1, 2, 3, 6, or 7? What did you say it was?
7.
7,
7.
1?
771.
771. Okay? I'm going to write it this way instead of times 10 to the negative 4th. There's your probability that if you roll 4 die, every single time you roll them, you're going to get a 3. Not very high. Part B, I don't want any 3s. So out of my 4 rolls, I want none of them to be 3s. Well, what's the probability I get a 3? 1/6. I want to do it 0 times. Probability I don't get it is 5/6. I want to do it 4 times. Well, 4 choose 0 happens to be 1. 1/6 to the 0 is 1. So really all you have to do is 5/6 to the 4th in your calculator to get this answer. .48? You actually have a 48% chance that you roll it 4 times, you will not get a 3. That's pretty high. Exactly 2 3s. So of my 4 rolls, 2 times I want to get that event. Well, I still have a 1/6 chance of getting it. I want to do it twice. I have a 5/6 chance of not getting it. I need to do that twice, because if I'm rolling it 4 times, it has to add up to 4. You're going to have to do all of this in the calculator. No shortcuts on this one. 4 choose 2 times 1/6 raised squared times 5/6 squared. 0.12. 12% chance that you will get exactly 2 3s. Suppose Michael makes 90% of his free throws. If he shoots 20 free throws, and if his chances of making each one is independent of the other, an assumption you might question in a game situation when people are yelling your name or trying to scare you. But anyway, what is the probability that he makes all 20 of them? Can you tell me how I set that up?
20.
20 choose 20 times
0.9 over 20.
0.9 raised to the 20th times
0.10 raised to 0.
0.1 raised to the 0 power. 20 choose 20 is 1. Anything to the 0 is 1. So all you have to do is 0.9 to the 20th power. What's the answer?
0.12.
0.12? Oh, that's higher than I thought. He's got a 12% chance that at all of them he makes. Well, he's a 90% free throw shooter, so that's pretty good. Exactly 18. 20 shots. He wants to make exactly 18. Percentage of making is 9 raised to the 18. Percent missing is 0.1 raised to the second. Run that one through your calculator. Okay. 29% chance that he makes 18 in between. Not so bad. At least 18. What does that mean, at least 18? 18, 19, or 20. So that would mean makes 18, 20, choose 18. I mean, we already did this one. 0.9 to the 18 times 0.1 squared plus, or he can make 19 of them. 20, choose, whoops, not a fraction. 20, choose 19, 0.9 raised to the 19, 0.1 raised to the 1, or he can make all 20 of them. 20, choose 20, I think we did this one already. 0.9 raised to the 20th, and 0.1 raised to the 0 power. But that's what you would have to do to get that answer. 18, 19, or 20th. Well, all 20 was this one. And exactly 18 was that one. So really the only thing that we don't know is this one right there.
This one's 0.2. So the total number is 0.68.
0.68 is the total? whatever this was, 0.68. So you've got a 68% chance of making at least 18. This binomial theorem and binomial probabilities work, like I said, on any two outcome event. If you have children someday, it's highly likely that you will either have a boy or a girl. How many children are you going to want?
Only last.
5 of them. Good choice. You want 5 children. If we wrote out the binomial expansion of this, b to the 5th plus 5b to the 4th g plus 10b cubed g squared plus, is it 15, the next one? Look on Pascal's triangle real quick. 15b squared g to the 3rd. Oh, it's 10. I added an extra 1 in there that I didn't need. 10 plus 5bg to the 4th plus 1g to the 5th. What this does right here, if you add up for me 1 plus 5 plus 10 plus 10 plus 5 plus 1. Add those numbers up. What do you get? 22. That's the total possible value. If you want to have exactly 3 boys and 2 girls, you have 10 out of 22 probability, or you have a 5/11ths chance that you will have exactly 3 boys and 2 girls if you have 5 kids. That's how binomial probabilities work.
Well, what if it's not 50-50, Chuck? Is that 49?
Now that's assuming it's a 50-50 chance on either one of them. That's assuming the 50-50. Still, a coin would be the same thing like that. Now the free throws with basketball, we'd have to set it up like we did right up here, just not a 50-50. Okay? All right. That's all yours.